And in the chapter 4, we're gonna skip first two sections. Well, first section we skip automatically because it's just an overview paragraph, and we will, of course, discuss that later. 4.2 we usually skip, so I don't worry about this as well. We don't need it, I guess. So now we're going to move to section 4.3 that deals with a formula. There is one very special formula which is being used for very special cases. Otherwise, this formula cannot be utilized. So this so-called binomial formula that deals with binomial distribution that says probability to get so many successful times when you repeat the same experiment if you do it number of times, which is called n. And if you're interested in some successes, so say x many of those successes, is going to be using the combinations, and there'll be a special situation with doing experiment and producing either success with probability p or a failure with probability complement q. And the probability p is raised to the power of number of successes and q power of n minus number of successes. So with this formula, we will practice visualizing that all exercises are really going to be the same, and that's very helpful. So I'm going to take an exercise and do it. And for that matter, I'm looking at, let's say, problem number 11 to start. That says n is equal to 2, and then we have also number of successes equal to 0, and probability of doing the experiment and producing a success is equal to 1%. So this is so-called special binomial experiment. When you do this once, and the chance to get the correct result, the one that you're interested in, is 1%. Let's say you're rolling a die and you're interested in getting 6 in it. So probability of success is going to be something, and probability of not success, the complement, or we call it as a failure, Q, is going to be the remaining. The complement is 1 minus, so it's going to be 99% in this particular case. Of course, it's not rolling a die, it's something else, but just to give a better example, I hope to understand better. So 99% is chance that you don't get it, and 1% the chance that you're gonna get it. So they're always gonna be complement of each other. And then to have a probability that you do it 2 times, this experiment, and in both times you don't get it, according to this formula above, is going to be number of combinations from 2 to get 0 successes, 2 trials, 0 successes, multiplied by probability of success, which is 1% raised to the power of, so it's same here, and the Q, which is the complement, which is 99%, which is going to be raised to the power of 2 minus 0. So it's according to the formula calculation. Of course, this kind of exercise you could have done earlier without using any formulas, you could have said, oh, I do my experiments 2 times, experiment once and then again, and chance that I don't make it is going to be 99%, right? 0.99, and means times that I don't make it again is another 99%. So this is like 99 squared. And if you decide to calculate this in the formula, the way to choose Nassim out of 2 trials, the combinations 2 comma 2 is going to be equal to 0. Let's see, really? Well, we can put it in a calculator and multiply by 0 power of any number is going to be 1. Any number to the power of 0 is 1 arithmetically. And the last 2 is going to be 0.99 squared, which is exactly what we had decided intuitively this has to be equal to. So either way, you're going to get the same calculation. So the answer is going to be the same. So let me go for my scientific calculator here. Scientific. And try to put in combinations 2 comma 0, which is going to be 1. And we'll see it now. So combinations, remember how to put them in 2 comma 0. So it is 1, and then you multiply this by 0.01 to the power, so use this power 0, and then put this on the ground, the cursor, and then times it again by 0.99, and I raise this to the power of 2 minus 0 power. I need to put it to the power. And power of 2 minus 0, which is just a 2, of course, and we got ourselves the answer, which is about 98%. So use of the formula only when you have a special type of experiment that you repeat in many times. Binomial experiment. So what's so special about it? It has only 2 results, either success or not, or failure. So for that case, you can use this formula when you repeat it again and again, and nothing changes from time to time. So this formula is nice to use, so I can use it again in exercise number 15. Just to show you that all exercises in this section are really the same. From perspective of using a calculator, well, you're just gonna put the numbers in such that n is 10, x, which is number of successes, is 4. So you do experiment for 10 times and interested in exactly 4 successful results. I say, what does it mean, successful result? Well, whatever you like to get. So that you calculate the probability of it. And 4 exactly successful trials, and probability of that result is going to be always given to you. It's 95% here. So not success means fail is remaining 5%, right? So it's like complement. We get 0.05. And then to get this calculated, I need P of 4. So I put 4 in the parentheses. And well, now we go with the formula. So n, see, I just plug in this formula numbers given. So instead of n, I put 10. Okay, 4 successes. So my x, which is going to be in 3 places, here, here, and here, is going to be 4. So I go times 0.95 raised to the 4th power. And then 5%, 0.05 raised to the power of 10 minus 4. And I know lots of people prefer to calculate this and get 6, which is pretty straightforward. So if you like that, you could calculate it yourself partially to help your calculator, but you don't need to worry about the calculator because it can do it. So functions, again, combinations, right? Return back to main, 10, 4. So this is what I multiply by 95 hundredths raised to the power of 4. And then bring this down again. I say, Alex, it's already calculated. No, not yet. We need to finish. 0.05, finish, enter. And I raise this to the power of 10 minus 4. I can say 6. So here is the chance. Here's the low probability, right? Power of -6 means I need to move my decimal 6 places to the left. So 1 place and then 5 more places. So 5 zeros will sit in front of that decimal. So I need to stick 5 zeros in front of the 267 ... This is a very low probability to get. You say, why is it so low, Alex? Well, 95% is a pretty good chance to get it. So it's very high level. So if you start to think of 95% successes in this times 10, that you repeat your experiment, that's going to be 10% of 95. So you should get that many successful times. And what they want you to do is just calculate, what if you have only 4 successful times? Is that likely? It is not. It's too low chance that you're going to get only 4 successes if you expect to get 9.5. Let me say, what is 9.5? Is it 9 or 10? Well, it's in between 9 or 10. So I should get 9 successful results if I repeat experiment 10 times, or I should get all 10 of them, because the chances to get success is pretty high. It's 95%. So what they ask is very unlikely. So it's just like 40% for success. And this actually just opened the door into the next section that says mean is number of times you do experiment multiplied by probability of success. So if I have probability 95%, and if I take it 10 times, that's what I expect. I expect the average. I say, I think you used to write mean with X that has a bar on the top. Well, here to identify that we deal with the binomial experiment, either failure or success. So it's like P and Q, right? And repeat the same thing again and again and again. So that's not very standard procedure, turns out, but it happens sometimes. So the average they identify with letter mu. It's a Greek letter mu. So it's like M, but the Greek, they like to have a wiggly thing. It's a mu. Well, that's like mean, right? Mean. So let me do another exercise and do this little addition to the story, because now we already have an idea about the formula. So I can use it in, let's say, American airline arrivals, the exercises that under this blueprint 21 through 24. So they say Find the probability at least 5 flights come on time. So in exercise number 21, they want to know at least 5. So what they talk about is either 5 or more, right? At least means not less. It could be that many or more, which is pretty standard, I think, type of question. So it's either 5 or means plus more, which is 6 or more. Actually, for this particular experiment, there is no more because they considered 6 arrivals total. So sample size is 6. And they also say the chance for the flight to be on time is 72 something percent. 723. Okay. So if we have this information, then what you can do is calculate your chances to get exactly 5 flights or to get more, which is 6 flights. So turns out when you have binomial experiment, you only care for the whole values for X. So you cannot have 5.5 flights to be on time. It's just not making sense, right? It could be either 5 flights or more, which is 6. So complement is what I need for using my new favorite formula. It's a Q, right? And this is going to be subtracting. So I produce point, what? Like 277, right? You can use calculator, make sure. So I have N, I have P, I have a Q, and here's my formula on the upper left corner. So notice I have everything I need. I'm just gonna use this formula 2 times. So we start with combinations, and then we go with the 6. N is 6. I choose 5 from it, right? 6, 5. And then P, which is 0.723, and raised to the power of 5. We say, why not 6? Well, because the power is X, the same number of selections. So you need to be careful when you put numbers in this formula. So 277, and the power now is going to be 6 minus 5. Okay? So I will put this in a calculator, and before doing it, I want you to look at the second calculation, how I'm going to use it in the formula. So I'm going to need to put now in the place of 5, 6. So it is really the same thing from perspective of calculators. So you just put a little different numbers. So again, 723 now is raised to the power of 6. Okay. And to finish up, I have 277. And this is also raised to the power of 6 minus, and now I go 6 minus 6. So that's going to be 0. Yeah, doesn't matter. Power of 0 is 1, so it doesn't matter to us. We'll let calculator now to simplify this for us. So let me go back to my favorite calculator and start to enter functions, right? Combinations, functions. 6, 5. So go back to main and put numbers 6, 5 parentheses times. And now I go 723. So I need to multiply by 0.723. So again, a nice part feature of this calculator is that you can see everything, because if you miss, enter something, you always be able to fix that because you see everything. So 277, and I raise this to the power, so power, and then it's 5 minus, right, 6 minus 5, 1. Okay, so this is what I produced, about 32 something percent, 0.328, dot, dot, dot. So I'll keep few decimals. And now I'm gonna need to change my previous calculation. And in order to change my previous calculation, I can fix this previous entry. Look at this. I can highlight 5. Now I need to put in a place of 5, 6. So I just delete the 5 and put 6. So I don't have to re-enter the whole thing again if I don't want to. You can do it if you want. It's up to you, but it's your choice. So 6 now is a power, and 211, 277 power of 6. And we got the other result. Let's write it down. So it's approximately about 0.143 approximately. Let's say if I care to get this thousands, and now I'm gonna get the answer. So now I'm gonna need to add this P05, 328, right? And then the other value, which is 6, which is 0.4143. So we can add the numbers and approximately see what the result is going to be. So if I add, I get like 1 and carry 1, so it'd be 7, that's 4. So about 47% chance that we'll get at least 5 arrivals on time. And this is what they wanted. So they say at least 5 of the 6 flights be on time. 5 or more. So please notice this is standard kind of procedure that we will be interested in when calculate our probabilities, because if 5 is what you're looking for, well, what if more? So it's even better. So 5 or better. So 5 or more. So one is, so what is this for? Well, maybe for planning those gate arrivals. If you ever fly someplace, you know what with me, it happens very often when I have to stay in the flight for a while. They say, oh, just wait, the gate is blocked or being used by some other plane. So they were not expecting so many arrivals on time. So if your flight is arriving on time or even early, sometimes it may happen the gate is not available. So it means they calculated chances of that to happen. Like in our case, it's 50-50. So they said, okay, we'll save a little bit on our whatever airport structure and have them wait. They just have them wait. But anyways, that's definitely disappointing. But they calculate the chances of this to happen. Sometimes it is, doesn't happen. So when you arrive, your gate is available right away. Means you fit into that probability, but sometimes it doesn't. So what's the chances of this to happen? Remember, we just noticed there is a average, which is mean, or n times p, that we calculate. So that's what we actually expect to happen. N times p. So in this case, n is 6 and p is 723 hundredths. So I guess I will use my calculator to get that. So if I multiply this together, I will see what number of flights we actually should expect to arrive on time. So let's multiply 6 by 0.723. and this is going to be 4.33. So what they expect is about 4 flights to be on time, right? So 4.3, so it's either 4 or 5. So I would say if you have your average 4.3, well, this is in between of 4 and 3 because I can have only the whole number of flights, either 4 or 5, right? It's in between 4 or 5. So we expect either 4 or 5. That's our average, that's our mean. But remember, there was also so-called standard deviation. So if you try to calculate standard deviation, and here it's also has its own notation for the standard deviation. There is a special formula in the case if we have binomial distribution, and they just give it to us, sigma, so I can try to put it down. So I will see the ballpark, how far to the left and to the right it extends the ballpark, because we know there's 4.3 is not possible. So, but depending on the level of spread, you might get all kinds of different answers. So I'm gonna calculate this square root, and then we'll make a little more sense out of that. So 723 is our probability to have a success, and the failure, remember we already have it here, it's complement of P, 277. So if I 277, so if I put this in my calculator, I will be able to see how far away from that mean we expect it to get. So I'm going to be taking the square root. That's something new. That's the next section I'm talking about already. 6 times 0.723 and then 0.277. So it's 109. What does that mean? Well, 109 is about one plane, right? A little bit more. And again, I'm trying to make sense from that. In this situation, we can have only either 4 planes or 5 or 6. So if that's our standard deviation, 109. So I can go by standard deviation to the left and to the right. If you remember, we already did it in the previous chapter. So when we saw standard deviation, so we have add in 1, so that will be like 5.4 approximately. And if I subtract 109, so that'd be like 3.1 or something, 3.2 approximately. So the actual situation that we will now expect is to get in between of 3.2 flights or 5.4 flights, which means that we don't expect that all 6 will be on time or only 3 will be on time. We expect it to be either 4 or 5 flights that arrive on time. And we just calculated that about 33% chance that 5 will come on time. The chance that 6 will come on time, so all of them will arrive on time, is low. It's 14%. It is possible, but it is low. Or 3, it is also going to be possible because 3.2 is very close to 3. So they expect it to be 3, 4, or 5 flights that will arrive on time. And based on that expectation, if the airport is operating with limited number of gates, it's not infinite number of gates, it's fixed. So they start to see how many arrivals they could possibly schedule within some time period, because there is not just one company, right? There are various airlines, so they try to see how they can accommodate those airlines the best possible way. So looks like that's very realistic kind of story, and now we're gonna enjoy some more of this in the next portion in the section 4.4. So besides using the formula, they add one part. They discuss these two new formulas, mean or standard deviation. Actually, they discuss more of them. And they just do this in pretty much every exercise. So let me try a couple of those. It's a nice and I would say pretty short section. So chapter 4 has already statistics in it. And in statistics, it's all about formulas. If you know the formula, you know how to do all the problems in the section because they're all the same. So you just put the numbers in the formula, and that's the result that you will get. And that's what makes it to be much nicer than mathematics. I'm talking about statistics. It's nicer because when you start to use statistics, you just plug numbers in the formula. In mathematics, you need to see which formula to use, so there's a lot. But here it's pretty straightforward. So let me try exercise number 5, let's say. Let's see, what about this? 4 and 3. Well, these problems you are gonna really put in the formulas right away. So in the section 4.4, we have two formulas. NP for mean and the square root for NPQ as a standard deviation. So these two calculations we're gonna produce in every exercise. So here just straightforward and a little story to entertain us, like in exercise number 5, that will deal with a favorite, with a multiple choice, or actually true-false test with number of questions equal to 10. So number of questions is always going to be n, which is 10. And true-false questions means that probability to get it right is 50%, and probability not to get it right is complement is also 50. So it's 50-50, right? P and Q are the same in this case, because if you have no clue what you're answering, not even reading their question, so 50% chance you guess it correctly and 50% you guess it incorrect, 50-50. So they say, how about mean and standard deviation? In part A, for this exercise, they want you to use these two new formulas for the mean and for the standard deviation. So I'm gonna use n equal to 10 and take a half of them. So if I guess, I will expect to guess half, or 5 out of 10. But you may get luckier or you may not, and standard deviation always shows that. So if number of questions is 10, then how far away from this we can get from 5 expected guesses? Well, looks like I may need to use a calculator here, or not really. Well, let us C. So I go to the let me see, sure. Get to my calculator. Square root, right? So extracting square root from 10 times 0.5 and then times another 0.5. And we get some kind of decimal that we will be using to see how far away we are. So to approximate where we actually expect it to be. And looks like if I go back to the textbook, it's question part B. Because in the part A, they told us to just find mean and standard deviation, and we did it, and that's all they wanted. So we got two answers, whatever it is, whatever they are, we just write them down. But now there comes an interesting part B that says, what if somebody wants to pass? They say, I'm very lucky, Alex. I'm passing everything, multiple choices. So what's the chances for that to happen? Or to get at least 7 correct answers? Well, I can first of all estimate that by using the fact that my mean was 5, right? And I expect to be by 1.5, 1.6 approximately, either to the left and to the right. Okay. So 1.6. If I decide to add it to 5, so that will be 6.6. Or if I subtract it from 5, it will be 3.4. So when you do the pure guess, and of course, I know that some students make sense, right? Don't do pure guessing, even though they say guess the answers, but they read them, they throw away the ones that are not making sense, and some answers sometimes they're not making sense right away, so you throw them away. So it looks like if you were doing pure guesses, then it's either 4 or 5 or 6 based on the standard deviation. And 3 is already out of range, and 7 is already out of range. So you're not expected to pass if you're doing pure guessing. That's the point. You can be lucky, you can get 6. Yeah, you can be very, very, very lucky and you can get 7 and pass it, but you can get also 4, you can get also 3 with the same level of a chance. So what they want is to see, so is it unusual to get at least 7? Well, you say, well, looks like it is, because what's expected is 6 or 5 or 4, so it is unusual. But you can actually calculate this using the previous story, previous section, the formula you can use. Looks like 4 times, because at least 7 means it's either 7 or 8. Please notice you will pass this if you get 7 or more, right? If you get more, it's even better. You're still passing it. So if you get 8, or if you guess 9, or if you guess 10, I'm not sure if I have room here. I'll try to fit it. So I can try to calculate these probabilities. And then I will also add them all together, because or 7 or means plus. So it just pile up. The chances will increase if I just care for guessing 7 or more, right? So from 10 questions, I'm trying to guess 7. And then the chances is 0.5 to the power of 7, and then 0.5 to the power of 10 minus 7. And this procedure needs to be done 4 times, but here it will be a replacer. Instead of 7, now I'm going to put 8, because now calculate what if you guessed exactly 8. We also passed. It is harder, but well, it is possible. Maybe chances are much lower, but it is still possible. So I subtract from 10, 8 in that column. Not sure why I put parentheses, but I just started to put parentheses. And so forth. So this will be 10, 9, right? See, instead of 8, I'll put 9, so it's 0.5 power of 9, and then 0.5 power of 10 minus 9. And finally, a very last one. Now instead of 10, I use, instead of 9, I put 10. Like that. So all these 4, I need to round and add. 0.5 power of 0. 10 minus 10 is, okay, 10 minus 10, just to make sure it all looks consistent. So it is tedious. So it was much faster to, of course, use the standard deviation to see it's not likely, but to be more precise, I can actually do the calculation, use my new favorite formula. And don't know if that's favorite, but it's tedious, but well, let's use it. So combinations. Now I need to go 10, 7. Excuse me. 10, 7. So try to get a calculator and see how you can use it. I guess it's, well, it is a skill to use your calculator correctly. I know everybody can use a calculator, but the question is, are you using it correctly? So this is 10 subtracted 7 is 3. So notice the chances of this is about 11% likely. Well, people say likely if you have more than 30%. It is possible to guess when you get lucky, but I guess it's not really likely. But one can say I have more chances if I guess even more. So instead of 7, if I added this, I put 8. And then for the powers, I need to also go 8 here and then 8 there. Okay. So that one is also minus. Subtracted from 10 is 2. So looks like now it is getting lower, of course, to guess more. You have less chances. So it's 0.439. So it's like 4, 3, so 4, 4, something like that, right? If I round to significant 3. So it's got like 4 times less chance. Okay, so we'll do it twice more to show you that this is getting even less chance, right? So I get power 9, and that's power of 1. So what is that? About 1%, 0.001. It's not even 1%, it's 0.1% to guess all 9 correctly. Not all 9, just any 9. And then finally, all 10. What's the chances to be extremely lucky you got all 10 of them guessed correctly? Well, not much of a chance, right? So it's 0, and I got, what is that I got? Power of -4, so I move decimal 1 place here, and then need 3 zeros, right, in front of that. 3 zeros. in front of that 9. So it's lower. So add them all together and see if that's likely. I say probably this could be the case, but could not be. So you better do a little study, I guess. But in the case if you couldn't, had some other priorities, it's, well, you can still try to guess and see what will come out. So I add this with 0, 0, 0, 9. Approximately, this will give us the result, which is about 16% chance. So 16% chance, or 0.01, 0.162 something, about 16% chance. Not very high, not very high. That's why we say it's unlikely, because 30%, the key number, the border number for the story. So 30%, if you did not get 30, we say it's unlikely. But again, it is still possible, because not likely is 5% or less. But here we have a little more, we have 16%, so it's possible, probably. And probably that's why I don't see many of true-false tests, at least in mathematics. So true-false, they don't ask, they ask multiple choice from A, B, C, right? So it's like up to E or up to D, so multiple choice. So I guess that's nice little story that concludes chapter 4. So I actually went through 2 sections, 4.4 and previous 4.3, and that's really all it is in the chapter 4. So I'm going to stop this recording with a good enough chunk of material for next time, for Monday.